For our last geometry to review, let's have a look at using Gauss's law to find the electric field near a uniformly charged plane with a charge density sigma. Remember, we already sorted out what this was equal to by thinking about the integrals. Now let's try it using Gauss's law. Gauss's law says that the net electric flux is the integral of the E dot dA equals Q enclosed over epsilon naught. E dot dA, that's the integral over some Gaussian surface, and Q enclosed is the charge enclosed by the Gaussian surface. The Gaussian surface is pretty important. Let's see how we're going to find that part out. Let's start to think about the electric field around a plane and how do we pick the appropriate Gaussian surface. So our plane just looks something like this. Yes, it is a little piece of Legos. What we know about the electric field of a plane is that if our plane has positive charge, the electric field vector sticks out in both directions. So it points up on the top and it points down on the bottom. That's what the electric field vector looks like. If we want to pick a Gaussian surface, what we generally do is pick something that matches the symmetry. The reason why we pick something that matches the symmetry is it makes it easy to do the integral. So something that would match the symmetry of a shape like this would be a box. Let's make our Gaussian surface a box where part of the box sticks off the top of the surface, like this, and part of the box sticks out of the bottom of the surface, like this. Okay, now when we go to do our integral, all of the vectors are either going to be parallel or perpendicular. So our electric field on the top points straight up like this. Then the area vectors on our little cube that points up out of the top, points perpendicular out of each side, and then for the front and the back, points front and back. So all of those vectors, when we do our integral of E dot dA, everything's either going to be perpendicular or parallel. So for us to find the flux is not going to be that difficult. Let's just add a drawing of that Gaussian surface to our picture here. I'll try it 3D, but it's not going to be that easy. So there's my box on the top surface sticking out, and it sticks out down on the bottom as well. Kind of like that. Hard to see. The 2D version is even easier. So it sticks up out of the bottom, comes up out of the top and out of the bottom. There's our Gaussian surface. So what we're going to do is we're going to figure out what is E dot dA for every surface of that cube, and we're also going to figure out how much charge is enclosed by it. Let's move on to the next slide to work on that part. Let's deal with our integral of E dot dA part first. If you look at our cube, you'll notice that a cube has 6 sides, so we're going to have to find the flux through the top, flux through the bottom, and flux through the side. Let's do the flux through each side first. So the integral of E dot dA, maybe I'll just write down the flux symbol first. So flux through the side equals the integral of E dot dA for one of the side faces of our cube. I'm going to try and draw it up here on the top picture first, the 3-dimensional. So I'll just pick that right-hand side. My area element sticks straight out to the right. On my 2D picture, that's probably even easier to see, dA. And our electric field vectors, they point straight up out of the plane. So what we see for the side face is that E and dA are perpendicular. So the integral of E dot dA is the integral of E times dA times the cosine of the angle between them, which is 90 degrees, equals 0. Now that's true for every face of the box. The front face, the dA points straight out, that's perpendicular. Left face, it points out to the left. Back face points straight back. So every one of those faces is perpendicular to the electric field vector. So the flux through every side is equal to 0. Okay, let's do the top next. Flux through the top is the integral of E dot dA. Let's get the angle on the top. I'll do it on my 3D picture first. We see that dA sticks straight up on the top. So those two guys are parallel. The angle between them are 0. Integral of E dot dA is E times dA times cosine 0. Cosine of 0 is 1. We know that electric field is a constant around that plane, so we've got E times the integral of dA, E times A. A is not quite as easy this time, so let's just leave it as an A for right now, and let's come back to it in a minute. We also need the flux through the bottom. So I'll draw that on my 3D picture. On the bottom face, the dA points straight down. My 2D picture, it points straight down. My electric field is also straight down, so my electric field, E dot dA, follows the steps as we did for the flux for the top, and what I get is E times A. If I want my net electric flux, then what I do is I add all those guys together. So my net electric flux is the flux for the top plus the flux through the sides plus the flux through the bottom, and I get 2 times E times A. Okay, that's my integral part added up. Now I have to find my charge enclosed. I'll go on to the next slide to do that part. So for my second part of my Gauss's law calculation is I need to find the amount of charge enclosed by my Gaussian surface, where these black cubes are my Gaussian surface. The charge inside the Gaussian surface is the charge on the part of the plane that's inside the surface. I'll shade that part in purple. So the charge on my Gaussian surface is whatever charge is on this part of the plane. Okay, how do I find the charge? Well, I know that charge is going to be density times area. When I'm talking about a plane of charge, I use surface area charge density, sigma, that's what's given. For area, I mean that part of area there, the area of the top face of my Gaussian surface. I called that A. Okay, and I used that in my previous calculations for the integral of E dot dA. Okay, I think I'm ready to put my Gauss's law expression all together. So my net electric flux is the integral of E dot dA, which is 2 times E times A. That's equal to the charge enclosed by the surface, which is sigma times A, divided by the constant epsilon naught. I see that I have an A on both sides. They can cancel. And then I'll solve for my electric field vector that tells me E is equal to sigma over 2 epsilon naught. Electric field is a vector. We know it goes out of a positive and it goes into a negative. Okay, after this review, we'll move on to do some slightly more interesting examples.